In this video, we're going to talk about how to do derivatives on your robot. Dynamics and other important robot concepts are often given to us in some sort of an equation form. And this is usually continuous space, has derivatives, has integrals in it, that sort of thing. Computers, on the other hand, usually need some sort of discretized input, so discretized form of the equation. And robots in particular tend to get their updates at discrete time steps. So not continuously, but every so often you'll get an update that contains the update for that entire time step, whatever that happens to be. So how do we convert this real-time, continuous time space to discrete but still real-time on the robot? Well, we use numerical integration and differentiation. And in this video, we're going to talk specifically about the differentiation part of this. So to start with, let's think about what is a derivative. So way back when you first learned about derivatives, you probably saw an equation that looked a lot like this that basically says we're going to take some function and we're going to take the value of the function at x, we're going to subtract that away from the value of the function at x plus some h, and divide that whole thing by h, so by the distance that it moved on the x-axis when you looked at that difference. And we're going to look at that and see what happens when h goes to 0, so when the limit of h is 0. And this is great, but this essentially means that we're looking at infinitely small time steps. And robots don't really like infinitely small time steps. We get these updates discretely. But when you were first learning derivatives, you probably came across something like this. So what happens if h is not 0, or not the limit as it goes to 0? What happens if h is some real number that's a little bit bigger? So maybe a few seconds, maybe a tenth of a second, that sort of thing. So in that case, we're going to look at this graph on the right-hand side here, where we look at f of x and f of x plus h, and we sort of just assume that that straight line between those two is the derivative that we're looking for. So it's not going to be exact, but it's going to give us a little bit of an estimate so that we can make some informed decisions later. As an example here, let's consider a robot where we get position updates frequently, but we don't actually have a velocity sensor on the robot. So maybe your robot's got a working GPS that tells you what position you move to from time to time, but the speedometer for some reason isn't working and GPS isn't giving you that. So how do you estimate velocity if you only have these position updates? So an example here, consider your duckybot, and this crude representation of a duckybot on the screen here. And let's say that at the initial time, 0, we're at some position. And then we move a bit. 2 seconds later, at time 1, we find that we've traveled 1 meter. So over this 2 seconds, we've traveled 1 meter. How fast were we going? Well, we know that the average here is just 1 meter divided by 2 seconds. We can say, v1 is equal to 0.5 meters per second. Now, this may not be exact. If you had to accelerate from a stop at the beginning and you accelerated the whole time, then your v1 velocity may actually be a full meter a second. If you accelerate very quickly, then it could be very close to 0.5 meters per second, but all we're doing here is getting an estimate. And normally we get updates more often than every 2 seconds, so normally this isn't really such a big deal. If we get updates every tenth of a second, then it doesn't matter nearly as much if we consider acceleration or not, because there's just not that much acceleration you do over a tenth of a second. So this robot moves a little bit further here. It's going to go for another 2 seconds until 4 seconds here, and we're going to find it only moved half a meter over this time. So half the distance in the same amount of time must mean it moved half the speed. So we can just take our delta t, which was 2 seconds, divide our distance by that delta t, and we'll get our velocity as 0.25 meters per second here. And again, if you have faster time steps, if you have less time in between these time steps, then you're going to get a better answer than this, but this is a good enough estimate for what we're looking at right here now for this example. So referring back to our initial example setup here, our position updates frequently, probably more often than every 2 seconds, but we don't have a velocity sensor, so how do we actually estimate this velocity? Well, here's some pseudocode that shouldn't be taken as actual code to copy-paste, but pseudocode that you can take a look at here and guide you through making your own system like this. So we're going to have 2 state variables here. We're going to have to know what our last position was and the time that that last position happened so we can do our calculations. And then really every time we get a new update, a new position update, we're going to estimate our velocity by saying what was the distance we traveled between that time and now, and how much time elapsed between that time and now. And we're going to divide those two things, so it'll just be delta distance over delta time, and return that. That's your estimate of velocity. So pretty simple. How does this work in real life? Well, the blue line here is the derivative of a sine, and the orange line is the numerical differentiation of that same derivative. They're pretty close. Now, this was using a finer resolution than every 2 seconds you get an update. This was looking at more like 1,000 updates per X tick on the bottom there, which is meaningless because it's just a sine wave. But you can still see the idea here. The numerical differentiation is just a little bit off from the actual differentiation, but it's close enough for a good estimate. So this is something we can use on robots to get an estimate of how fast we're going, or how fast an error is changing, or any of these other things where you might need a derivative that's not perfect, but it's a good enough estimate. So this will get you going through controls and odometry type problems.